Hi everyone, my name is Kian, and today I will talk about our work on quantifying intrinsic value of information of trajectories. And this is joint work with John Crum and Cyrus Shahabi. Let's start with some motivations. We all know that location data is a very important type of data, and in our work, trajectory of type location data is defined as a sequence of location measurements, and it has a very broad range of applications like disease control or transportation. So trajectories are very valuable. So we want to use the notion of value of information to quantify how much valuable it is. And traditionally, VOI is defined like how much a decision maker is willing to pay for information prior to making decisions. But a trajectory's VOI can also a very critical piece of metadata that indicate its intrinsic value for a variety of tasks, like selling it, share it, store it, or use it for training machine learning model. And of course, VOI depends on the use and user of the data. However, from the owner's perspective, a trajectory also contains an intrinsic value of information, and because it contains quantified locations of the owner over space and time. So for example, we can use number of measurement as the VOI because we often see that more measurement tend to give more information. So our goal is to find a principled approach to quantify the VOI of trajectories from the owner perspective. And there is many challenges in this problem. First is that many characteristics of trajectory itself can contribute to its VOI, like size, duration, or how the measurement distributes over space and time. So we need a fair way to compare wildly different trajectory against each other. It can be short or long, sparse or dense, noisy or accurate. Another aspect is that the trajectory can be degraded for different purpose. So for example, for privacy purpose, noise can be added or measurement can be removed. In our work, we use Z to show denote the degraded version of trajectory S. Another important aspect is that the owner may also assume that there can be prior information or prior knowledge about the trajectory. This prior information omega can be like publicly available data or previously released data of this owner. And we represent this prior knowledge as the prior probability distribution for each measurement given this prior knowledge. So our problem setting is that we want to find a principled approach to quantify the VOI of trajectory from the owner perspective that capture all of these categories of trajectory characteristic, prior knowledge, and degradation effect. We'll go deeper into each of them. First, for trajectory characteristic, we consider the following characteristic of a trajectory that need to be taken into account by a quantifying method. So the size, durations, spatial and temporal distributions, and measurement uncertainty. For prior knowledge, we said that the owner may assume that the recipient may already have some prior knowledge about the trajectory, and that prior knowledge need to be taken into account by a quantifying method. About trajectory degradations, a less degraded trajectory would tend to give us more information, and we want to capture it as well. There can be different types of degradations of a trajectory, and here we consider three common types of degradation. Perturbation, adding noise, truncation, cut the trajectory, and uniformly subsample. So we have many characteristics we want to capture. In our paper, we evaluate several baseline methods from simple to complex, and we found that many times they cannot capture these characteristics. Sometimes they only partially capture these characteristics, and sometimes they can capture some of the characteristics, sometimes with some caveats. And more detail on how we assign these marks can be seen in our paper. And we see that a common issue with those previous methods is that they use a discrete location measurements as the representation of trajectory, which make them ignore information between two consecutive measurements, and also difficult to compare different characteristic, different trajectory against each other. That's why we introduced information gain framework or IG framework. And this framework, instead of using these discrete location measurements as a representation of a trajectory, we use a canonical representation which is continuous in time with continuous estimates of mean and variance, like the figure on the right, where the estimated mean is the blue line and the blue area is the estimated variance. And this representation is very crucial for comparing wildly different trajectories and comparing new data against prior data. We use a reconstruction method to transform trajectories from the discrete form to these representations. And our implementation use Gaussian process, but our framework accepts any reasonable reconstruction method that can produce continuous time probabilistic predictions. So after having the representation, we view the VOI as how much the trajectory data can help us reconstruct the owner's locations, or how much it helps to reduce uncertainty of estimating the location of the owner in continuous time. And we used information gain to quantify that reduction. As an example, let's say before the prior information omega, let's say, is nothing, we don't have anything, and but we can still reconstruct the locations, and because we don't have any good prior information, the reconstructions has a very large variance, and the predicted location, the mean is doesn't change. Then when we have Z, we make the reconstruction as the figure on the top right, and we then compare the two reconstructions and find the uncertainty reduced as the red area not covered by the blue area here. So this is an overview of our framework. So when we have both when we only have prior information and when we have new data, we reconstruct using that data and comparing the reconstruction with prior information and reconstruction when we have new data, see how much uncertainty reduced, and use IG to quantify that reductions using that IG as the VOI. A bit more detail on how to calculate IG at a time point t, small t. So with the prior information omega, we can have a prior probability distribution pxi given omega for the location of the owner at that time point. Then the owner may assume that after receiving Z, the recipient can reconstruct the locations in continuous time and have a posterior distribution Px given Z and omega. Then the IG would measure the reductions of uncertainty at this time point, where the uncertainty is quantified using differential entropy. And this is the equation of the differential entropy of a continuous random variable. Then we can integrate the IG over a time period t, capital T, and use that as the VOI. And in our work, we use the data containing the trajectory as the time period capital T. We evaluate the IG framework both qualitatively and quantitatively using the Spearman's rank correlation coefficient and on the GeoLife dataset, which is a very large trajectory dataset. Here is a quick illustration of how IG can capture characteristics of trajectories. And here we have two data points, and of course we do reconstruction and calculate IG, and we have IG about 9.2. And when we have the same two data points but with much lower uncertainty, then the IG increase up to about 16.9. Then it's the same two data points, but now they are much further apart, and they can help us reduce a lot of uncertainty between them. So IG increase to 29.1. When we have the same start and end point, but we have more data points, of course more data points give it more information, and IG increase to about 32.1. Now the same data point, a number of data points and the same duration, but now the data points more distribute more evenly over time, and it can help us really reduce a lot of uncertainty between them. And IG increase to 45.1. And now, when the data points distribute more evenly over space, over the y-axis, as you can see, then it can also help us reduce the uncertainty in between them. However, sometimes when the data points jump really widely over the space, then uncertainty can increase, and IG at that time may not be able to capture that capture that case. Quantitative evaluation also shows a strong correlation between IG and trajectories characteristics. So that's why we want to say that the IG framework can capture size, duration, temporal distribution, and measurement uncertainty, but it can only partially capture spatial distribution. For prior knowledge and degradation, we show here the experiments for perturbation. Here we on the x-axis we have the total noise where we want to add to the each data point of the trajectory, and on the y-axis we have the IG. And consider different prior knowledge. The first one is what we call uninformed prior. So basically, we don't have any prior data. So we assume that the prior distribution of locations of the owner is a Gaussian distribution with extremely large variance, like the owner can be anywhere. The others two informative priors are basically previously released data of this owner, like the same trajectory, but they previously released with 400 meter noise for each measurement. And we can see that when we have more degradations, the IG getting smaller. From left to right, the degradation increase, and the IG decrease. This match our intuitions that when we have more degradations, we have less information. And we also see that with better prior knowledge, so we also have smaller IG. So it matches our intuitions that when we already have a good prior knowledge, the new data would not give us as much as information as before. And the same trends also hold for in the percentage point of view. More experiment can be seen in our paper. And that's why we say that the information gain framework can capture prior knowledge and degradation. So that is our information gain framework, which we show that it can capture majority, almost all of the characteristics that we are interested in, and it shows as a good candidate for quantifying intrinsic value of information of trajectories from the owner perspective. With that, I want to thank you and happy to answer questions.